So just a couple quick corrections on the solution to mission 2. I'll probably repost it, but I just want to, in case you've already printed it out or looked at it or something, and were confused, understandably so. Let's see here, I made a couple mistakes, one more serious than the other. But the first mistake I made was on problem 26. So on problem 26, my solution, I inadvertently did the limit as x goes to 0, but I was supposed to do the limit as x goes to the natural log of 2, right? And so when we do that, we get 1/2 e to the natural log of 2 plus e to the minus natural log of 2, which is 1/2 2 plus e to the natural log of 1/2, which is 1/2 of 2 plus 1/2, which is, 5/4. I think. Or it could be wrong. Let me see here. No, it's 5/4. Yeah, 5/4. So one of you had like 3/4. That was just a sign error. You put a plus, or you put a minus where you wanted to have a plus. But my solution is 0. I took the limit as x goes to 0 because I just ignored what the problem actually said, right? So that's my bad. A more serious mistake was made in problem 27. So problem 27, I was looking at the limit, as x goes to 5 of the square root of x plus 11 minus 4 divided by x minus 5, and I should have got that. I should have seen that worked out to 1/8. So I will post a solution. I will post a correction to that. I made a stupid algebra mistake there. I kind of got distracted midstream and forgot to multiply the numerator and the denominator both by the same thing. I just multiplied the numerator alone, which you can't do. For problem 29, one of you got infinity. But the reason you got that was on problem 29, you copied down 1/t² rather than 1/t, and that changes the problem. But otherwise, your work was right, so I didn't count off because it was good. That's all I think I got to say about that, except, one other important comment. Problem 32, if I have an x there and I took off points, I should give it back to you because problem 32 didn't make sense. I was supposed to have x goes to minus 2 as the limit there, not x goes to 2. Otherwise, the problem's not interesting. All right, well, that's all I got to say about that. So let's go back. I told you guys I'd leave some time here to talk about mission 3, so let's do that. What do you guys have questions about mission 3? For problem 38. Yeah, mm-hmm. So yes, so hint for problem 38. So you have f of x equals to g of x for x not equal to 2 or 3. All other x, right? And you also can notice that the formula for f of x is continuous, like at all other values. Like, in other words, you could calculate that the limit if you simplify the formula for f of x, right, you'll get something that's clearly continuous at everywhere except for 2 and 3. So you can show that, what I'm trying to say is, you can argue that the limit as x goes to a of g of a, which is just equal to the limit as x goes to a of f of x, not a, f of x, is just equal to f of a for a not equal to 2 or 3, right? For a not equal to 2 or 3, you can just plug in those values. The denominator function in that thing, if you factor it, it's x minus 2 times x minus 3, right? In the formula. If you look at the formula, the denominator factors into x minus 2 times x minus 3, right? So everywhere except for there, we could just plug in the limit point, right? So it's clear that the limit as x goes to a of g of x is equal to g of a, which is, by the way, equal to f of a, which is, by the way, g of a, provided that you're away from these points. Okay, so we already have satisfied that the limit of g of x is equal to g of a for every x except for 2 and 3, right? So the question asks you, what values do you have to give to g of 2 and to g of 3 to make g a continuous function, right? So what I'm saying is it boils down to just fixing, all you have to do is specify the values of g of 2 and g of 3 and you're done because of this observation, right? So you need to say the limit, what we need is that the limit as x goes to 2, right, of g of x is equal to what? You need that to be equal to g of 2, right? And you need the same. Yeah. But you can calculate these, right? Because the limit as x goes to 2 involves values close to 2 but not equal to 2. And you know the formula for that because it's just f of x. G of x is equal to f of x for x not equal to the 2 or 3, right? So you can replace g of x with the formula for f of x and calculate the limit. That has to be whatever g of 2 is. I mean, you straight up know that g of x equals to f of x, which is equal to, 10. I'm trying not to work out the problem stuff, right? Let me say Pac-Man over Ghost. So when you calculate the limit as x goes to 2 of g of x, you can calculate the limit as x goes to 2 of the formula for f of x. And in order to calculate that limit, you're going to have to do algebra to simplify that. Not a lot. But you can't just plug 2 or 3 into the equation. You have division by 0. You have to take the limit. But yeah, I mean, if that's what you mean. Mm-hmm. The question is, what do we mean by continuous, right? Continuous means that the limit of the function is equal to the value of the function at the point, for each point in the domain, right? I mean, this is a theorem that we have. Some people would take it as the definition. I gave you the definition in terms of epsilons and such, right? But it is a close cousin, if you will, to say that, f, or in this case, g continuous on the reals means the limit as x goes to a of g of x is equal to g of a for each a in the reals. So for this problem, that limit's already clear as long as a is not equal to 2 and 3. For 2 and 3, we actually have to calculate the limit because you can't just plug in the points there because you have division by 0 in the formula for f. You're still plugging the number in once you do the simplification inside the limit, right? So suppose we had f of x equal to x squared times x minus 3 over x squared minus 9. All right? And this is for x, for the domain of f being, say, 0 to infinity. Okay? So, well, except for one thing, right? I can't have 3. So 0 to 3 union with 3 to infinity. So I could say find g from 0 to infinity, continue it to the reals, continuous such that g of x equal to f of x for x not equal to 3. That would be like the problem I've assigned. I'm not going to work a problem in class like every homework problem. Like, you have to think, generally speaking. Like, we go over concepts. You have to apply those concepts to problems. There's just not enough time to cover every single kind of problem type in class, right? Like, just as a generic, like, posture of this class, homework versus class time, there will be homework problems that I don't work in class, right? It's a university course. You have to, like, apply the concept to solve the problem. But that said, I will work this one. I can't spell. I think there's a U here, right? Well, I try to do some, but yes, ultimately, we all teach ourselves. That is true. So here, what do? So this formula is what? We have x squared, x minus 3. We factor that, x minus 3 times x plus 3. So what can we do? Cancel the x minus 3, right? So this is x squared over x plus 3. For what? That's only true when what? For x not equal to 3, right? That's the string attached there, right? So you can calculate then the limit as x goes to 3 of g of x is equal to the limit as x goes to 3 of what? Well, remember we have g of x equal to f of x for x not equal to 3, right? So I can replace this with the formula for f of x. But I might as well use the simplified formula to make life easier. So I have x squared over x plus 3. Then what? Then we can plug in the value, whatever it is. We get 9 over 6. And so that's what I have to make g of 3 equal to in this example in order to make this a so-called continuous extension of the function. So graphically here, what's going on in this one is this function, well, it's kind of hard for me to, well, fine. The graph of the problem that I've assigned you is easier than this one. This is, how would you graph x squared over x plus 3? I don't think I've talked about it this semester at all. So x squared over x plus 3 is an example of a rational function that's an improper rational function because the numerator has larger degree than the denominator. Well, I don't want to get too far into this, but essentially what would happen here, and I'm just going to be very sketchy here because I don't want to spend the 5 minutes it would take to graph this, but let's see here. It starts where? At 0, right? and then it goes up. I mean, actually, this thing, once x is really, really large, this thing is approximately like the graph of x, right? If you think about this, if x is really, really big, x squared over x plus 3 is basically like x over x because the 3 is irrelevant. So after a long time, this just becomes y equals x. So it's got some kind of funny business, but then like asymptotically, eventually it goes to this. But what happens is there's a hole in the graph at 3, right? There's a hole in the graph at 3. But this is crudely speaking what the graph looks like. But that's the significance here, is that for this function, there's a hole in the graph at 3 because the function's everywhere else continuous. There's just this one point where we have a hole in the graph. That's like what's going on with this example. And your homework problem's the same, except there are 2 holes.
So we did on like in our homework, we do g of x to 3 and g of x to 2.
G of 2 would be the limit as x goes to 2 of g of x.
Yeah, so like you plug in 2 for one of the equations and 3 for the next.
Right, but again, after you simplify in the limit, right? Other questions? So you had another question, I think, right? Well, what do you want me to do? I mean,
You just told me you don't feel like explaining these in class, so I'm not going to ask.
that's not at all what I'm saying. I'm saying that we won't be able, I wouldn't expect that every problem that's in the homework is in class. That's all I'm saying. I mean, if you ask me about it and we have time, I'll answer it, right? But there won't always be time for every kind of homework problem in class. But there's always time in my office hours for more. A question? Does anybody else have a question? 41. So do you remember we had some problems? I don't know if we had a problem exactly like this, but when we talk about intermediate, first of all, IVT is intermediate value theorem, right? And so we're looking at this equation, 4x minus the cube root of x over 4 equal to 1. So, and I said, hint, think about the interval 0 to 4. So what we want to do is, what's the intermediate value theorem tell us? It tells us something about a continuous function on a closed interval, right? So this one, the thing that jumps out at me is this right here I should think of as my function, right? We can call this, say, f of x or g of x, whatever you like. And my first thing would be say, okay, that's a function, and it's a continuous function on 0 to 4, right? How do I know it's a continuous function? Well, we've got the square root and the cube root. Those are both continuous as long as we're feeding the square root non-negative things. And since x is from 0 to 4, this is continuous on 0 to 4, right? All right, so that's observation number 1. And then, so number 1, I see that. Number 2, let's check out what is f of 0. We have what? Square root of 4 times 0, which is 0, minus the cube root of 0 over 4, which is 0. What is that? Yeah, 0. So yeah, f of 0 is 0. Not equal to 1. I mean, that, all right, so that. And, well, the next thing I would do would be to try f of 4, because that was the hint, you know. F of 4, what's that equal to? Square root of 16, right? 4 times 4 is 16, minus the cube root of 4 over 4, which is what? 1. So square root of 16 is 4. 4 minus 1 is 3, right? Notice, what do we have? We have f of 0 equals to f of 0, right? Is less than 1, right? Which is less than f of 4, which is equal to what? 3, right? I'm sorry, I seem to be solving your homework problem. But when I make up similar homework problems, bad things happen, you know? I end up creating a function which is too complicated or something. Anyway, so what can you tell me? So 1 is a value between f of 0 and f of 4, right? So the intermediate value theorem says what? So as you're thinking about this homework problem, the first thing you should do is to read the intermediate value theorem and make sure you understand what it says, right? Because that's kind of the whole point of this problem. The conclusion is, okay, so by the intermediate value theorem, there exists some constant c, right, in the open interval from 0 to 4, such that what? F of c equals to that intermediate value, which in this case is 1. But that's exactly what we want, right? Because if you set x equals to c, you've solved that equation, just like you want. So that's problem 41? 41, yeah. How about problem 42? Let's talk about problem 42. Problem 42 is a little bit different, isn't it? There we're supposed to look at solving e to the x equals to x to the 4th for x greater than 0. So we're supposed to show that there's a solution to this for x greater than 0. So when I wrote my solution yesterday, I found a negative solution by accident pretty easily. But that doesn't help. I mean, so this one here, can you just, what would you do? I mean, this is an intermediate value problem, but this one we have to use a little trick. What we have to do is take the given problem and convert it to one that I can think of as a problem about a function. See, I can convert this to e to the x minus x to the 4th equals to 0, right? If I can solve that equation, I can solve the equation above. But the advantage of the equation I just wrote is I can think of it in terms of values of a function. I can think of this as like f of x, right? And that's continuous. on, well, it's a continuous on the reals. So in particular, it's continuous on any closed subset of the reals that you want to pick. So now you guys just have to figure out some values to plug in to see that that function changes from negative to positive or vice versa. I mean, the value of the function, you have to find a find a point to plug in that it changes from positive to negative. Or vice versa. Anyway, I'll let you figure out those values, but you can try looking at some different numbers. Other questions? Now, Taylor, I think the thing that I have most neglected in lecture in terms of like a question that's on mission 3 is the problem about graphing. The one that's about graphing functions and tangent derivatives to functions. Well, it's actually not a question about graphing the derivative function yet, but problem 46. Problem 46 is actually an interesting problem in the sense that it has all of the different ways that a derivative might fail to exist. So like 3 of those, the answer is does not exist. There's only one which is an existent one, all right? And the reason is actually different for all 3 cases where it doesn't exist in that problem. All I'm trying to say is, I'm not trying to say I'm not going to solve homework problems in here necessarily. I'm just saying don't wait for lecture to try to do something. Like, you guys can do things before I finish discussing something. I mean, that's part of this course. Goodness gracious, so much chalk. If my intention was not to answer any of your questions, I would have just gone on and not spent time on homework today, All right. So let me remind you, definition. If, A is an element of the domain of a function, and f prime of A equals the limit as h goes to 0 of f of x, f of A plus h minus f of A divided by h exists, then f is differentiable at x equals to A. In this case, we say y equals to f of A plus f prime of A times x minus A is the tangent line to y equals f of x at point of tangency a comma f of a. One of the first theorems we can prove about a function which is differentiable at a point is that it's also continuous at that point. So this is a theorem. If f prime of a, if f prime of a exists, then the limit as x goes to, we could write it this way, as h goes to 0 of f of a plus h is equal to f of a. So remember, this is another way of expressing continuity. Remember, we have the substitution. We could also write this as the limit as x goes to a of f of x equal to f of a. All right? So how would we prove this theorem? So I guess I would start with the limit as h goes to 0 of f of a plus h, maybe, and try to go from there. Feels wrong. So a second here, let me get back on the beaten track. See, where were we? We're in chapter 4. I think at the moment, all we've done is really look at difference quotient examples, right? This is actually proposition 4.14. Where'd my chalk go? I have to be careful. This is one of those ones I can go in circles if I'm not careful on. So let me follow my notes here. And so what I say is 0 is equal to the limit as h goes to 0 of h times the limit as h goes to 0 of f of a plus h minus f of a over h. Now that's a fair statement because we're assuming that f prime of a exists, right? And the limit as h goes to 0 of 0 of h is 0. That's like this is clearly 0. This is f prime of a, which is given, right? So these are two limits which exist. Therefore, I can use the product of the limits rule to combine them. By the way, this is not my favorite proof of this result, but it's a proof, so we'll take it for now. And so inside the limit, h is not equal to 0. We can cancel them. Right? So since the limit as h goes to 0 of f of a is equal to f of a, it follows that the limit as h goes to 0 of f of a plus h is equal to f of a. All right, so that concludes my proof of this assertion, which is that differentiable implies continuous, right? So just remember this, differentiable implies continuous at a point. So in your homework problem, that one I asked about, number 40, yeah, 46 was it? In problem 46, notice that at -1, what happens? If you look at -1, there's a jump in the graph, right? The function's not continuous there. So a sort of a corollary to this theorem is this. If f not continuous at x equals to a, then f prime of a does not exist. So if you've got a point in your graph which has a point of discontinuity, in that case there's a jump in the graph in 46, it can't be differentiable at that point because it's not continuous. The other place where the derivative doesn't exist is if there's a kink in the graph, like if there's like a corner in the graph, like absolute value. We talked about that Friday a little bit. And then the third way is if there's a vertical tangent, right? So vertical tangent, a graph with a vertical tangent. For example, if you look at f of x equal to the cube root of x, this guy has a vertical tangent right here. So you can prove that f prime of 0 is actually like infinity if you calculate the limit as x goes to 0 of f of x minus f of 0 over x minus 0. In this case, that would be the limit as x goes to 0 of the cube root of x divided by x, which, by the way, is what? One over the cube root of x squared, right? And that, my friends, is infinity. So if the difference quotient works out to infinity, then we say the function has a vertical tangent at that point. That's also a place where the derivative does not exist. So I think with that said, I think everything else in that mission should make sense. And if it doesn't, you can ask me about it now. Still have a couple minutes. Have I done? Oh, there it is. All right, I'm going to move on here and talk about the next section, which is section 4.2, if I can never find where I put my notes. So up till now, I've been talking about the derivative at a point, right? Whether it does or doesn't exist. And the next thing that we like to do, in fact, we'll be doing this for the rest of the course, really, is be thinking of the derivative as a new function that we can build from a given function. And goodness gracious, I just cannot find my notes. The thing is, I just had them. Ah, here it is. So section 4.2. Uh-oh, I have somehow gone unplugged again. Know what's going on here. Yeah. Need to hire like a student worker just to watch this extension quarter. Let's see here. Okay, so right here I have the definition of the derivative at a point, right? So here's the definition of the derivative as a function. If f is function on the reals, then f prime is a function on the reals where f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h for all x in the domain of f such that the above limit exists. So all I'm really saying is that the derivative function is itself defined by the derivative at a point. Just that's the new function. So and we have other notation that we use for this. So f prime of x, of course, we can also denote by df dx. We also denote this by d dx of f of x. These are all notations for the same thing, the derivative of the function at a point. If we want to go back to f prime of a, we can do this. F prime of a is equal to df dx. And then this, people use this long bar like that. It's an evaluation bar. You do evaluated at x equals to a. So these are all notations for the derivative. So let's look at an example. F of x equal to the square root of x. We can calculate the derivative function for this. What's the domain of this function as it stands? The natural domain here is 0 included to infinity. So we can try to calculate f prime of x for all those x. Let's do it. F prime of x, limit as h goes to 0 of the square root of x plus h minus the square root of x divided by h. All right? Now, to calculate that limit, what are we going to do? What trick are we going to use? We're going to use that rationalization trick, right? So let's see here. So what we're going to do is we're going to do square root of x plus h plus the square root of x divided by the square root of x plus h plus the square root of x. And so that's a nice trick because when we do that, what happens? Yeah, square roots cancel out. So we get x plus h from the product of the two square roots there, right? And like you said, we get plus this product minus that product. They cancel out. So we get minus x. Now, I think if you look at my notes, I have about 3 more steps there written out. But the x's cancel. The h's also cancel. What are we left with? Right? And so take the limit as h goes to 0. What do we get? Yeah. Yes. Well, the h goes to 0, right? So, I mean, I guess I could write square root of x plus 0. Oh, okay. You're taking the limit, you're using x for the limit rather than h, yeah. Understandable. So that is 1 over 2 times the square root of x. And so there you go. We have now earned one of our important results to know from this course. Going forward, this is something you should have memorized, really, for future use. There it is. The derivative of the square root function is 1 over twice the square root function. Now, in other words, f prime of x is 1 over 2 square root of x. Now, can you tell me for what x that's true? X an element of where? What's the domain of the derivative function here? What's this thing look like? Square root function, right? What happens at the end point? Actually, if you look at it carefully, you've got a vertical tangent right there, right? So the derivative has a smaller domain than the function itself. It goes from 0 to infinity. 0 is not included. Now, I'm actually not going to define the derivative at endpoints of a function. We just don't have a need for it, and so I won't bother. But all right, well, next up here, let's try another function on for size. How about 1 over x squared? Actually, let me do something easier for a second here. What if we had f of x equals x? What's the derivative of that? We're supposed to take f of x minus what? F of x plus h. F of x plus h minus f of x divided by h, right? So for this rather silly case, that's very easy to calculate. That is x plus h minus x. So the x's do what? They cancel, right? And then the h's reduce. And we get limit as h goes to 0 of 1, which is 1. So this calculation shows us that the derivative with respect to x of x is equal to 1. Of course, you could also write this result as dx equals to 1, and it gives you the idea that we're just canceling fraction, right? Like we're just canceling numbers. But of course, that's not actually the case, right? I mean, in this course at least, we're defining the derivative as a limiting quotient. But back at the time of Newton, Leibniz and such, they actually did think of these as like a quotient of what are called infinitesimals. And even now, there are schools where it's taught this way, where instead of using limits, they use something called non-standard analysis, where they take the real numbers and they adjoin to the real numbers these things called infinitesimals. And then if you do that, you can build derivatives from actual quotients of these infinitesimal numbers. But the downside of that is then you have to construct the infinitesimal numbers carefully, and that's actually somewhat technical. So and any way you slice it, there's difficulty. I mean, but I think the way we're doing it is good. It's the standard way, and so there it is. So next example, what if we had f of x equal to 1 over x? Could you calculate the derivative of this? So pretty much everything we're doing here, curses. I've worked myself into the corner. Well, not yet. I'm working on it, though. All right, so f prime of x, limit as h goes to 0 of 1 over x plus h minus 1 over x all divided by h. Now what should we do? Every last one of these is type 0 over 0, right? So, I mean, there's always algebra to do. So what I'm going to do is make a common denominator of x minus parentheses x plus h divided by h times x plus h. So I made a common denominator in the numerator, and then I went ahead and brought the fraction into just a single fraction, right? Like the denominator of the numerator becomes the denominator, and what was in the denominator just stays put and multiplies that. Anyway, again, the x's cancel and the h's cancel, and we're left with an expression that's not indeterminate. It's just something we can actually plug in h equal to 0 for once we see through this. Now I can plug in h equal to 0. I get minus 1 over x times x plus 0, which is, of course, minus 1 over x squared. So therefore, we have that d dx of 1 over x is equal to minus 1 over x squared, which is, again, something you would do well to commit to memory. Maybe we should try a polynomial, you know? Let's try out x squared. Let's calculate the derivative of x squared. So you guys work on that while I work on erasing this here. How are you going to start? So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h, right? So f prime of x, limit as h goes to 0 of, in this case, x plus h quantity squared, right? Minus f of x, which is x squared, divided by h. So what happens? We've got x squared plus 2xh plus h squared minus x squared, all divided by h. Notice that the x squareds cancels again, right? How does this simplify, this expression? See, these guys, they cancel. And so what we have, limit as h goes to 0 of 2x plus h. Where did the what? The other h. So, fine, I'll do another step here. So this is 2x plus h times h divided by h. So I can factor h out from those two terms, and then I can cancel them. Which is 2x. So derivative with respect to x of x squared is 2x. Can you guys see a pattern emerging? So yeah, let's look at it. So derivative with respect to x of x to the power 1 is equal to 1. The derivative with respect to x of x to the power 2 was 2 times x to the 1, right? The derivative with respect to x of x to the 1/2 power was 1/2 x to the minus 1/2, if you look at it, right? This is 1/2 x to the minus 1/2, right? The derivative with respect to x of x to the minus 1 power, that was, our example over here. We had minus 1 over x squared, right, which is minus 1 x to the minus 2 power, right? So if you start looking at this, you see, well, this is really 1 times x to the 1 minus 1 power, right? And this is really 2 times x to the 2 minus 1 power. And this is really 1/2 x to the 1/2 minus 1 power. And this is really minus 1 times x to the minus 1 minus 1 power. There's a pattern. And the pattern is this. d dx of x to the power n is equal to n times x to the n minus 1. This is the so-called power rule. So now we could prove this for natural numbers, either using like the binomial theorem. Do you guys know the binomial theorem? Nope. So binomial theorem says this. In our context, x plus h to the n power, it works out to x to the n plus n x to the n minus 1 h plus a bunch of stuff plus n x h to the n minus 1 plus h to the n. So if we look at, f of x equal x to the n, then f of x plus h minus f of x is equal to, so see what happens is you have this whole term is this guy, right? And this is exactly x to the power n. So that and that cancel, and what you're left with is n x to the n minus 1 h plus a bunch of stuff